The universe was never supposed to be quiet. Not in the way it is now. If you could stand at the edge of the observable cosmos, an impossible vantage point, suspended beyond galaxies and time, you would not hear silence. You would hear motion, expansion, a low, omnipresent stretching, as if the fabric of reality itself were being pulled apart by unseen hands. Space is growing, not explosively, not violently, but relentlessly, and it is accelerating. This is the first wrong thing. For most of human history, we assumed the universe was either eternal and static or expanding but slowing down. Gravity, after all, is a hoarder. It pulls, gathers, binds. Stars should tug on stars. Galaxies should drag on galaxies. Expansion should decelerate under the collective weight of everything that exists. But it doesn't. Instead, the universe is flying apart faster with every passing second, as if gravity has been outvoted by something far more powerful, something invisible, pervasive, and profoundly indifferent. We call it dark energy, a name that explains almost nothing and hides the depth of our ignorance behind two familiar words: dark. Not because it is evil or shadowy, but because it refuses to interact with light. Energy. Not because we understand how it works, but because we have no better category for what it does. Dark energy makes up roughly 70% of the entire universe. Everything you've ever seen, stars, planets, people, memories, wars, dreams, accounts for less than 5%. The rest is dark matter and dark energy. And of the two, dark energy is the more disturbing. Dark matter binds galaxies together. Dark energy tears the universe apart, and it is winning. The story of dark energy begins not with a discovery, but with a mistake, or rather, with a correction of one. In 1917, Albert Einstein introduced a term into his equations of general relativity that he later called his greatest blunder: the cosmological constant. At the time, Einstein believed the universe was static. To prevent gravity from collapsing everything into a single point, he added, a repulsive force, a kind of mathematical pressure pushing space outward. When astronomers later discovered that the universe was expanding, Einstein abandoned the idea. The cosmological constant was unnecessary. Gravity alone could shape a dynamic cosmos. For decades, the matter seemed settled. Then, in the late 1990 seconds, astronomers looking at distant supernovae noticed something unsettling. These exploding stars, used as cosmic mile markers, were dimmer than expected. Too dim. The universe had expanded more than it should have if expansion were slowing down. The only explanation was unthinkable. Expansion wasn't decelerating. It was speeding up. Something was pushing the universe outward, not just counteracting gravity, but overwhelming it on the largest scales imaginable. Einstein's abandoned idea returned from the dead, no longer a mathematical convenience, but a terrifying necessity. The cosmological constant had a new name now: dark energy. Unlike anything else we know, dark energy does not clump. It does not gather into stars or galaxies. It does not dilute as space expands. Instead, it appears to be a property of space itself. The more space there is, the more dark energy there is. And as space expands, dark energy creates more expansion. A feedback loop written into the structure of reality. At small scales, dark energy is weak. Inside galaxies, gravity still dominates. The Milky Way will not be torn apart tomorrow. The atoms in your body are safe. For now, but beyond galactic boundaries, across the vast cosmic voids where matter is thin and distances are obscene, dark energy rules absolutely. It stretches space between galaxy clusters. It widens the gaps between islands of matter. Over time, those islands will drift beyond each other's reach, disappearing behind horizons from which no light can ever return. The night sky is growing poorer. Every second, galaxies slip beyond the observable universe, their light stretched into invisibility by the expanding fabric of space. Future civilizations, if any exist, will see fewer stars, fewer galaxies, fewer clues that anything ever existed beyond their local group. Dark energy is not just destroying the universe. It is erasing the evidence that it ever existed at all. There is something deeply unsettling about a force that does nothing, interacts with nothing, and yet determines the fate of everything. Dark energy does not announce itself. It does not flare or roar. It simply acts, quietly and continuously, indifferent to time, life, or meaning. And it raises a question that physics cannot avoid. Is dark energy constant? If it is truly unchanging, a fixed property of empty space, then the universe will continue to expand forever, growing colder and darker, stars burning out one by one until only black holes remain. Eventually, even they will evaporate, leaving a thin, cold soup of particles drifting through an endless void, a slow, silent death. But if dark energy evolves, if its strength increases over time, the future becomes far more violent. Space itself could be torn apart. In a catastrophic event known as the Big Rip, galaxies would dissolve, solar systems would unbind, atoms would be ripped asunder. As the expansion of space overwhelms every force that holds matter together, reality itself would be shredded. We do not know which future awaits us. We don't even know what dark energy is. Some theories suggest it is vacuum energy, a consequence of quantum fields fluctuating in empty space. Others propose new dynamic fields permeating the universe, slowly changing over time. Still others argue that dark energy may not exist at all, that our understanding of gravity breaks down on cosmic scales, and we are misinterpreting the data. Each explanation carries its own discomfort. If dark energy is vacuum energy, then theoretical predictions overshoot observed values by an absurd margin, off by a factor of 10 to the power of 120, the worst mismatch between theory and observation in all of physics. If it is a new field, it introduces particles and forces we have never observed. If gravity is wrong, then one of the most successful theories in human history is incomplete. Every option implies a fundamental ignorance at the heart of reality. And yet, dark energy does not wait for our understanding. It continues its work regardless, stretching space, thinning matter, isolating galaxies, pulling the universe toward an unknowable end. We are passengers in a cosmos dominated by a force we cannot see, cannot touch, and cannot explain, a force that shapes the destiny of everything while remaining stubbornly silent. The universe was never supposed to be quiet, but dark energy does not need noise to be powerful. It only needs time. To understand how deeply wrong this quiet acceleration is, we have to return to the beginning, not to the Big Bang itself, but to the assumptions we carried afterward. For most of the 20th century, cosmology was a simple contest between motion and gravity. The universe exploded into existence. Matter flew outward, and gravity worked tirelessly to slow the expansion down. The only open question was how strong gravity was compared to the initial blast. If there was enough matter, expansion would eventually halt and reverse. The universe would collapse in a fiery big crunch, time folding back into itself. If there wasn't enough, expansion would continue forever, but always slowing, coasting toward an asymptotic stillness. Those were the options. Acceleration was not on the menu. Everything we knew about gravity argued against it. Every mass pulls on every other mass. As structures form, gravity strengthens locally. Over billions of years, clumping should dominate. Expansion should lose. And for a long time, the universe seemed to agree. When Edwin Hubble first measured the recession of galaxies, the discovery was shocking enough. Space itself was expanding. Galaxies were not flying through space away from one another. The space between them was growing. The farther away a galaxy was, the faster it appeared to recede. But there was no reason to think this expansion was speeding up. In fact, early data hinted it might be slowing, exactly as gravity demanded. Then technology improved. By the late 20th century, astronomers had learned how to use a specific kind of stellar explosion type, IA supernovae, as cosmic yardsticks. These events occur when a white dwarf star steals too much mass from a companion and detonates with a remarkably consistent brightness. Measure how bright it appears, and you know how far away it is. Measure its redshift, and you know how much the universe has expanded since the light was emitted. Distance and time, written in starlight. Two independent teams began surveying these explosions in distant galaxies, expecting to measure the deceleration of cosmic expansion. They expected gravities, fingerprints in the data. Instead, they found something else. The supernovae were too faint, not slightly, systematically. Across vast distances and times, the universe had expanded more than gravity alone could explain. The farther back they looked, the slower the expansion had been. Somewhere in the past, the universe had crossed a threshold. Expansion had learned to run. This was not a subtle effect. It was not a statistical fluke. The data were stubborn, repeating the same message over and over again. About 5 billion years ago, the expansion of the universe began to accelerate. Something changed. That timing matters. 5 billion years ago, the universe was already mature. Galaxies had formed. Stars burned steadily. Heavy elements were being forged in stellar cores. In one spiral galaxy, orbiting an unremarkable star, planets were assembling. On at least one of them, life was stirring toward complexity. Dark energy did not dominate the early universe. Back then, matter and radiation ruled. Gravity sculpted structure, pulling gas into filaments and knots, igniting stars and assembling galaxies. Expansion slowed as expected, but as the universe expanded, matter became more diluted. Galaxies drifted farther apart. Gravity's reach weakened on the largest scales. Dark energy did not dilute, it waited. Eventually, the density of matter dropped low enough that dark energy, whatever it is, rose to dominance. And once it did, the rules changed. Expansion stopped listening to gravity's objections. Space began to stretch itself faster and faster, driven not by an explosion, but by a persistent, uniform pressure embedded in the vacuum. This tells us something unsettling. Dark energy is not a leftover from the Big Bang in the same way radiation is. It does not fade with time. It becomes more important as the universe grows older. The future belongs to it. On the largest scales, gravity has already lost. Galaxy clusters are the last great structures. Gravity can still hold together. Beyond them, space expands too quickly. Filaments thin, voids widen. The cosmic web unravels strand by strand. In billions of years, distant galaxies will slip beyond our cosmic horizon. Their light will never reach us, no matter how long we wait. They will still exist, but for us, they will be gone, causally disconnected, erased by expansion. This is not movement through space. This is space itself pulling away. Imagine ants on a rubber sheet, being stretched evenly in all directions. The ants are not walking away from each other, yet the distance between them grows. If the sheet stretches faster and faster, no amount of crawling can compensate. That is our situation on a cosmic scale. And here is the deeper problem. We do not know why the acceleration began when it did. If dark energy is a constant property of space, why did it wait billions of years to dominate? Why is its strength tuned so delicately that it becomes important only after galaxies form, but before the universe grows too old? This coincidence has a name: the cosmic coincidence problem. It asks an uncomfortable question. Why now? Why do we happen to live at the precise epoch when matter and dark energy have comparable influence? Too early, and dark energy would have prevented structure from forming at all. Too late, and the universe would be an empty, dark wasteland with no observers left to ask the question. Some physicists whisper the word anthropic. Perhaps many universes exist, each with different strengths of dark energy. We find ourselves in one where the value allows complexity, because only such universes can be observed. Others recoil at this idea. It feels like surrender, a retreat from explanation to selection bias, but the numbers are brutal. Quantum theory predicts vacuum energy values wildly larger than what we observe. If dark energy is vacuum energy, something cancels it almost perfectly, leaving behind a tiny residue that just happens to shape the fate of the cosmos. No known symmetry explains this cancellation. No known mechanism demands it. It simply is. And that controls everything. Dark energy does not form waves we can easily detect. It does not produce particles we can trap. Its effects appear only when we step back far enough to see the universe as a whole. It reveals itself not in laboratories, but in the slow drift of galaxies and the faint dimming of ancient explosions. It is cosmic-scale evidence of ignorance. We are used to discovering forces by watching things collide, bend, or glow. Dark energy refuses all of that. It announces itself only through absence, through the way gravity fails to slow the universe down. This makes it uniquely dangerous to our understanding, because if the dominant component of the universe operates by rules we do not know, then every prediction about the far future rests on fragile assumptions. A constant today may not be constant tomorrow. A gentle acceleration could hide a growing instability. The universe may be quieter than expected, but quiet does not mean safe. And as we look deeper into space, measuring expansion with greater precision, we are really asking a single, fragile question. Is dark energy stable? Or is this calm merely the prelude to something far worse? There is a profound strangeness in the idea that empty space can weigh something, not metaphorically, not poetically, physically. In everyday life, emptiness is the absence of things. A vacuum is what remains when matter is removed. But in modern physics, emptiness is not empty at all. It seethes with activity, quantum fields fluctuating, particles appearing and vanishing in fleeting instants. Even in the darkest void between galaxies, space is alive with invisible motion, and according to our best understanding, that restless vacuum has energy. This is where dark energy becomes deeply unsettling, because energy does not just sit there. In Einstein's theory of general relativity, energy curves space-time. It tells space how to stretch, bend, and evolve. Matter pulls space inward. Radiation pushes outward briefly, then fades. Vacuum energy, if it exists, does something stranger still. It pushes forever. In Einstein's equations, pressure is as important as density. Positive pressure, like that inside a star, adds to gravity's pull. Negative pressure does the opposite. It creates repulsion. Dark energy appears to have negative pressure. So negative, in fact, that its gravitational effect is repulsive on cosmic scales. It does not pull matter together, it pushes space apart. This is not an analogy. This is math. If dark energy is the energy of empty space itself, then the universe is expanding not because something is pushing galaxies outward, but because space prefers to grow. The vacuum resists being compressed. It wants to stretch. And the more it stretches, the more vacuum there is. The implications are difficult to overstate. In this picture, nothingness is the most powerful thing in existence. But here is the problem. Quantum field theory, the framework that describes the subatomic world with astonishing accuracy, predicts vacuum energy. Every quantum field contributes a baseline energy even in its lowest possible state. Add them all up, and you get a value for the energy density of empty space. That value is catastrophically wrong. Depending on how the calculation is done, theoretical predictions overshoot the observed value of dark energy by factors of 10 to the power of 60, 10 to the power of 90, or even 10 to the power of 120. This is not a small discrepancy. It is the largest known mismatch between theory and observation in the history of science. If quantum theory were a map and dark energy were a city, the city would be located in a completely different universe. Something is cancelling almost all of the vacuum energy, leaving behind a tiny residue that just happens to dominate the universe today. We do not know what that something is. We do not know why the cancellation is so precise. And we do not know why it leaves behind exactly the amount required to accelerate expansion at the observed rate. Physicists have proposed mechanisms, symmetries, hidden dimensions, fields that adjust themselves dynamically. None have survived experimental scrutiny. The universe appears finely balanced on a knife's edge, and we do not know why. This has led some to an uncomfortable conclusion. Perhaps there is no deeper explanation. Perhaps the value of dark energy is environmental, like the height of mountains or the depth of oceans. Different regions of a larger multiverse may have different vacuum energies, and we inhabit one of the rare pockets where the value allows structure and observers. This idea is not popular. It feels like giving up, but it refuses to go away. If dark energy were even slightly larger, galaxies would never have formed. Matter would have been torn apart before gravity could do its work. The universe would be smooth, empty, and lifeless. If it were slightly smaller, gravity might eventually reverse expansion, leading to a cosmic collapse. The fact that it sits in the narrow range that allows billions of years of structure and complexity is either an extraordinary coincidence or a clue we do not yet understand. What makes this worse is that dark energy is uniform. No matter where we look, its density appears the same. It does not clump around galaxies. It does not vary from one cosmic void to another. It is evenly spread throughout space, like a background hum beneath reality. This uniformity is what makes it so hard to study. There are no gradients to follow, no concentrations to probe, no local experiments to run. We can only observe its cumulative effect over billions of light years. This turns the universe itself into a laboratory. By mapping the distribution of galaxies, measuring the cosmic microwave background, and tracking how structures grow over time, cosmologists try to infer the properties of dark energy indirectly. They look for tiny deviations from expected patterns, subtle clues hidden in the large-scale geometry of the cosmos. So far, dark energy has been stubbornly boring. Every measurement is consistent with a simple cosmological constant, a fixed energy density of space that never changes. This simplicity is, paradoxically, suspicious. Nature rarely chooses the simplest option without reason. If dark energy truly is constant, then the universe's fate is sealed. Expansion will continue forever. Galaxies outside our local group will disappear. Star formation will slow and cease. The cosmos will drift toward a state of cold, dilute isolation, a slow fading. But if dark energy is not constant, if it evolves over time, then all bets are off. Even small changes in its equation of state could dramatically alter the future. A strengthening dark energy could lead to runaway expansion. A weakening one could allow gravity to regain control. There is even the unsettling possibility that dark energy could change sign. If that happened, repulsion would become attraction. Expansion would halt. Collapse would begin. The universe could end not with a whimper, but with a reversal. Right now, we cannot rule any of this out. We live in a universe where the dominant component is invisible, poorly understood, and potentially unstable. Our best models fit the data, but only because we have tuned them to do so. This is not ignorance at the edges. This is ignorance at the center. Dark energy is not a small correction to our picture of the universe. It is the picture. Everything else, galaxies, stars, planets, life, is a minor perturbation riding on top of a vast, stretching vacuum. We are used to thinking of space as a stage on which the universe unfolds. Dark energy suggests the stage itself has intentions, and whatever those intentions are, they are not aligned with permanence. There is a limit to how much of the universe we can ever know. Not because our instruments are insufficient or our theories incomplete, but because the universe itself is erasing information as it expands. Dark energy does not merely stretch space, it builds horizons, boundaries, beyond which events are forever inaccessible. This is one of its most subtle and devastating consequences in a decelerating universe. Light emitted anywhere, given enough time, can eventually reach anywhere else. Space may grow, but expansion slows. Distances increase, then stabilize. The cosmos remains, in principle, knowable. An accelerating universe breaks that promise. When expansion accelerates, there are regions of space moving away from us faster than light, not because they are traveling through space at impossible speeds, but because the space between us and them is expanding too quickly for light to cross. Signals emitted beyond a certain distance will never reach us, no matter how long we wait. That distance defines the cosmic event horizon. It is not a wall. It does not glow or shimmer. It simply exists as a mathematical boundary, silent and absolute. Beyond it, the universe continues, but it might as well not exist as far as we are concerned. Every second, the event horizon encloses us a little more tightly. Galaxies that were once visible slip beyond it, their last photons stretched into invisibility. Over cosmic time, the observable universe shrinks, not in physical size, but in accessible content. The universe is forgetting itself. This forgetting has profound implications for knowledge and memory. Cosmology depends on light from the past. The farther we look, the earlier we see. The cosmic microwave background, the afterglow of the Big Bang, is a snapshot of the universe when it was just 380,000 years old. But in a dark energy-dominated future, even that ancient light will be redshifted beyond detection, its wavelengths stretched until they are larger than the observable universe itself. The evidence of the beginning will vanish. Imagine a civilization arising tens of billions of years from now. They will look into the night sky and see only their local galaxy, perhaps a few merged remnants of nearby systems. No cosmic background radiation, no distant galaxies, no Hubble expansion. To them, the universe will appear static, eternal, and alone. They will have no observational evidence that a Big Bang ever occurred. Dark energy will have rewritten history. This is not speculation. It is a prediction grounded in our best models. Acceleration isolates regions of space, turning once connected domains into causally disconnected islands. Each island becomes its own universe, sealed off from the rest. In time, even the concept of cosmology becomes impossible. This is a quiet apocalypse, not of destruction, but of erasure. And it forces us to confront a deeper question. What does it mean to understand a universe that actively hides itself? Physics has always relied on the assumption that with enough patience and ingenuity, the laws of nature can be uncovered. Dark energy challenges that assumption. It imposes a fundamental limit on observability, not through complexity, but through expansion. There are things we will never see, not because we lack the technology, but because the universe will not allow the information to reach us. This has consequences for more than astronomy. In quantum theory, information is sacred. It cannot be destroyed. It can be scrambled, hidden, transformed, but not erased. Yet cosmic horizons appear to remove information from our accessible universe. Matter and radiation cross the horizon and never return. Where does that information go? This question echoes one of the deepest puzzles in physics, the black hole information paradox. Black holes also create horizons. Objects fall in, information disappears from view. Hawking radiation suggests black holes evaporate. But what happens to the information encoded in what fell inside? Dark energy creates a similar problem, but on a universal scale. Our universe has a horizon, like a black hole turned inside out. Some physicists suspect the connection is more than superficial. The entropy associated with cosmic horizons suggests that space-time itself has microscopic degrees of freedom we do not yet understand. Dark energy may be telling us something profound about the quantum nature of space and time. Or it may be exposing a flaw in our assumptions. Perhaps acceleration is not caused by a mysterious energy at all. Perhaps it is a sign that gravity behaves differently on the largest scales. General relativity has been tested exquisitely in the solar system and around black holes, but cosmic distances are another regime entirely. If gravity weakens or changes form beyond a certain scale, the observed acceleration could be an illusion, but modified gravity theories come with their own problems. They must reproduce all the successes of general relativity while explaining acceleration without dark energy. So far, none have done so convincingly without introducing new complications. Dark energy remains the simplest explanation, and simplicity, in this case, is terrifying, because a simple cosmological constant offers no drama, no turning point, no rescue. It implies a universe that accelerates forever, erasing structure, memory, and connection until each surviving island is alone in a sea of expanding nothingness. Stars will still live and die. Planets will still orbit. Life may continue for a time, but the larger story will be gone. The universe will not end in fire or collapse, but in isolation. Every observer, trapped within a shrinking bubble of accessible reality, unable to know how vast and rich the cosmos once was. Dark energy does not destroy matter directly. It destroys context. And in doing so, it reshapes not just the future of the universe, but the limits of meaning within it. So far, dark energy has been quiet, steady, almost polite in its destruction. But the universe has a history of surprises. Everything we know about dark energy comes from a brief snapshot of cosmic time, a few billion years, in a universe nearly 14 billion years old. We observe its effects today and project them forward, assuming its behavior remains unchanged. That assumption may be our greatest gamble. To describe dark energy, cosmologists use a single parameter, known as the equation of state parameter, usually written as W. It relates pressure to energy density. For ordinary matter, W is 0. For radiation, it is 1/3. For a true cosmological constant, W equals -1. -1 is special. It produces exactly the kind of constant, unchanging acceleration we observe. Space expands exponentially. Distances grow, but structures remain intact locally. The universe fades slowly. But what if W is not exactly -1? What if it is slightly greater, or worse, slightly less? If W is greater than -1, dark energy weakens over time, acceleration slows. Gravity may eventually reassert itself. Expansion could coast, or even reverse. But if W is less than -1, the situation becomes catastrophic. This hypothetical form of dark energy is called phantom energy, and it does something deeply unnatural. Its energy density increases as the universe expands. The more space there is, the stronger the repulsion becomes. Acceleration feeds on itself. In a phantom energy universe, expansion does not merely continue forever, it diverges in finite time. There is a countdown to destruction. The end of that countdown is known as the Big Rip. At first, the universe looks much like it does today. Galaxies drift apart. The night sky grows emptier. But beneath the calm, dark energy is intensifying, stretching space ever more aggressively. Then, one by one, the thresholds fall. Galaxy clusters are the first to go. Gravity can no longer hold them together. Galaxies that once orbited one another drift apart, their mutual pull overwhelmed by the expansion of space itself. Next, individual galaxies unravel. Stars no longer remain bound. The Milky Way dissolves into a cloud of isolated suns, each receding from the others, as space expands between them. Later still, solar systems break apart. Planets lose their orbits. Earth drifts away from the sun, not pushed by an explosion, but carried by the expanding fabric of space. Finally, in the last moments, even atoms are not safe. The electromagnetic force, which binds electrons to nuclei, is overwhelmed. Protons and neutrons are torn apart. Space expands faster than the forces that define matter. Reality loses cohesion. This is not a heat death, not a collapse. It is a tearing, a literal ripping of space-time at every scale. The Big Rip is dramatic, but it is also deeply uncertain. Current observations do not require phantom energy. Most measurements are consistent with W equal to -1, but the error bars are wide enough that we cannot exclude a small deviation. And a small deviation is all it would take. This uncertainty exposes a fundamental weakness in our cosmic foresight. We cannot experiment on the universe. We cannot wait billions of years to see what happens. We infer the future from limited data, filtered through theories we know are incomplete. Dark energy forces us to confront a future we cannot test. Even worse, it reveals how fragile structure truly is. Everything we consider stable galaxies, stars, atoms, exists only because the forces that bind them are stronger than expansion. Change that balance, and permanence vanishes. This raises an unsettling thought. If dark energy can strengthen, can it weaken? If it can evolve, what mechanism governs its evolution? We often speak of the laws of physics as fixed, eternal, unchanging. But dark energy may be telling us that even the vacuum is dynamic, that the properties of empty space can drift over cosmic time. If so, then the universe is not governed by a single, immutable script, but by a set of conditions that can shift, with consequences that cascade across reality. Some models imagine dark energy as a slowly rolling field, similar to those thought to drive cosmic inflation in the early universe. In these models, today's gentle acceleration could be the echo of a much more violent process, a field sliding down a potential landscape, its energy changing gradually. If that field reaches a different state, the universe could undergo another phase transition. The last time that happened, space expanded exponentially, wiping out pre-existing structure and setting the stage for everything we see today. There is no guarantee it cannot happen again. This is the hidden menace of dark energy. Not that it is destroying the universe now, but that it introduces instability into the foundation of reality. A constant universe is predictable. A dynamic vacuum is not. And yet, there is a strange comfort in the Big Rip. It is dramatic, final, conclusive. Compared to an eternal, empty expansion, a universe stretched thin and cold forever, the Big Rip offers an ending, a moment where everything stops. Perhaps that says more about human psychology than physics. We crave narratives, beginnings and endings, arcs that close. Dark energy may deny us that satisfaction. It may simply continue, silently, endlessly, stretching space until meaning itself feels diluted. Or it may surprise us. We do not know which. All we know is that the force shaping the ultimate fate of the universe is invisible, pervasive, and only barely constrained by our measurements. And it is not done with us yet. Dark energy announces itself only through consequences. It leaves no tracks in detectors. It does not scatter particles or bend light in ways we can isolate. There is no experiment we can build on Earth that will summon it into view. If dark energy had a signature, it would be written across billions of light years. So cosmologists learned to think bigger. To measure dark energy, they turned the entire universe into an instrument. They map the positions of galaxies. They track how clusters grow. They study the faint afterglow of the Big Bang. Each observation adds a pixel to a vast, slow-moving picture. One of the most powerful tools in this effort is the cosmic microwave background, the oldest light in the universe. Tiny temperature fluctuations in this radiation encode the conditions of the early cosmos. They tell us how much matter exists, how space is curved, and how fast the universe expands today. Dark energy leaves its imprint there indirectly. It alters the geometry of space, changing the way light travels across the cosmos. It affects how structures grow, suppressing the formation of large clusters by accelerating expansion. Another key method is baryon acoustic oscillations. In the early universe, matter and radiation were tightly coupled, oscillating like sound waves in a dense plasma. When the universe cooled enough for atoms to form, those oscillations froze in place, leaving a characteristic scale imprinted in the distribution of galaxies. That scale acts as a cosmic ruler. By measuring how it appears at different distances and times, astronomers can reconstruct the expansion history of the universe. Dark energy reveals itself in the way that ruler stretches. Then there are supernovae, the original messengers of acceleration. Each explosion is a beacon from the past, a timestamp marking how much the universe has grown since the star died, individually. These measurements are imprecise. Together, they form a web of constraints that narrow the possible behaviors of dark energy. So far, every thread points to the same conclusion. Dark energy looks like a cosmological constant, but looks can deceive. All of these measurements are statistical. They rely on assumptions about how galaxies trace matter, how light propagates through space-time, how astrophysical processes evolve. Systematic errors lurk everywhere. And even if the data are perfect, they tell us only what dark energy has done in the recent past. They do not tell us why. This is why new experiments are being designed with almost obsessive precision. Space telescopes will map billions of galaxies across enormous volumes. They will measure weak gravitational lensing, the subtle distortion of galaxy shapes, by intervening matter to track how structure grows over time. Growth is key. Dark energy does not just change distances, it changes how quickly matter collapses under gravity. Two models with identical expansion histories can predict different growth rates by comparing both. Cosmologists hope to distinguish between dark energy and modified gravity. This is detective work on a cosmic scale. And yet, there is a haunting possibility that all of this effort will lead to a dead end. That dark energy truly is constant, featureless, and irreducible. That no matter how precisely we measure it, there will be nothing more to learn. That would be unprecedented. In physics, deeper measurements usually reveal deeper structure. Atoms gave way to nuclei to quarks, forces fractured into symmetries and fields. Dark energy may be different. It may be telling us that the vacuum itself has a fixed energy, set by unknown physics at scales far beyond our reach. If so, then understanding it may require a theory of quantum gravity, a framework that unifies general relativity with quantum mechanics. Such a theory remains elusive. String theory offers one possible path, predicting a vast landscape of possible vacuum states, each with its own value of dark energy. In this view, our universe is one bubble among many, its properties determined by chance rather than necessity. But string theory has yet to make testable predictions in this domain. The landscape is too vast, the possibilities too numerous. Dark energy may remain an orphan, connected to deep theory but never fully explained by it. And still, we measure, because the stakes are too high not to. Dark energy determines the ultimate fate of the universe. It defines the horizon of knowledge. It may hint at new dimensions, new fields, or new principles we have not yet imagined. It also humbles us. For all our technological prowess, we are trying to understand a force that dominates the cosmos by watching galaxies drift ever so slightly faster than expected. We are inferring the nature of reality from whispers written in ancient light. This is science at its most audacious and its most vulnerable. We assume the universe is comprehensible, that patterns exist, that explanations await discovery. Dark energy tests that faith. If it turns out to be simple and constant, then the universe is accelerating toward isolation, and we may never know why. If it turns out to be dynamic, then we are living through a transitional epoch, one whose consequences we can only dimly foresee. Either way, we are embedded in a story much larger than ourselves. When faced with something that refuses to be seen, physicists have learned to ask a dangerous question: what if it isn't there at all? Dark energy is the name we give to an effect, not an object. It is a placeholder, a way of saying something is causing this acceleration and we don't know what. That leaves open a radical possibility. Perhaps nothing is pushing the universe apart. Perhaps gravity itself is failing. General relativity has passed every test thrown at it for more than a century. It predicts the bending of light, the ticking of clocks in orbit, the ripples of space-time from colliding black holes. On human and stellar scales, it is flawless. But cosmic scales are different. General relativity was never designed with an accelerating universe in mind. It assumes space-time behaves the same way everywhere, governed by equations derived from local observations. Extrapolating those equations across billions of light-years may be a mistake, one we have simply been lucky enough not to notice until now. In this view, cosmic acceleration is not caused by dark energy, but by a breakdown of gravity over vast distances. This idea is deeply unsettling. Gravity is not just another force. It defines geometry. It tells space and time how to behave. If it changes character at large scales, then the foundation of cosmology cracks open. Modified gravity theories attempt to make this idea precise. They tweak Einstein's equations, adding extra terms, extra dimensions, or extra fields that only become relevant when space-time is extremely stretched. Some theories imagine gravity leaking into higher dimensions, weakening its grip on our universe. Others propose new fields that mimic dark energy's effects without invoking vacuum energy at all. On paper, these models can reproduce acceleration. In practice, they struggle. Any modification to gravity must satisfy a brutal set of constraints. It must explain cosmic acceleration and reproduce every successful prediction of general relativity in the solar system, in binary stars, around black holes, and in gravitational waves. Most fail quickly. Those that survive do so by hiding their differences. They include mechanisms that suppress deviations from Einstein's theory in dense environments, revealing themselves only in the emptiest regions of space. This makes them nearly impossible to test. Ironically, the emptiest places in the universe, the vast cosmic voids, may hold the key in these regions. Matter is sparse, gravity is weak, and any modification should become visible. By studying how galaxies move near voids, or how light bends as it passes through them, cosmologists hope to catch gravity in the act of misbehaving. So far, it has not. Every new observation tightens the noose. Every precise measurement of structure, growth, lensing, and expansion pushes modified gravity models into narrower corners. Dark energy survives not because we like it, but because gravity refuses to break. And that brings us back to the most uncomfortable conclusion. The universe may truly be dominated by something that is not matter, not radiation, not force, but a property of nothingness itself. Empty space has weight. Empty space has pressure. Empty space decides the fate of everything. This realization forces a philosophical shift for centuries. Physics focused on objects, particles, fields, interactions. Space was a backdrop, a passive arena. Dark energy turns the stage into the main character. It suggests that space-time has internal structure, degrees of freedom, perhaps even dynamics we barely glimpse. What we call vacuum may be as rich and complex as any substance, governed by laws we do not yet know how to write down. If that is true, then understanding dark energy is not just another problem to solve, it is a doorway. On the other side may lie quantum gravity, the unification of space, time, and matter into a single framework. Or it may lie a deeper truth, that some aspects of the universe are not derivable from first principles, but are contingent, accidental, selected. That possibility is hard to accept. Science is built on the belief that reality is ordered, that explanations exist. Dark energy challenges that belief by sitting at the center of everything while offering no clues to its origin. It does not glow. It does not clump. It does not speak. And yet, it dictates the future. Perhaps the most unsettling aspect of dark energy is not what it does to the universe, but what it does to us. It reminds us that we are latecomers in a cosmos whose rules were set long before we arrived and may not care that we are here at all. We observe acceleration and ask why. The universe responds with silence. And still, we keep watching. Because somewhere in that silence, encoded in the slow drift of galaxies, the faint shear of lensing, the pattern of ancient light, there may be a message we have not yet learned how to read. Dark energy may be indifferent, but it is not meaningless. There will come a time when the universe is no longer bright, not suddenly, not violently, but gradually, inevitably, as dark energy stretches space and isolates what remains. The stars we see now are living on borrowed time, not because they will all explode or collapse, but because the conditions that allow stars to form are disappearing. Star formation requires density. Gas clouds must cool, collapse, and ignite. Expansion works against all of this. As galaxies are pulled apart and gas is thinned, fewer stars are born. The universe grows older, redder, quieter. In a dark, energy-dominated cosmos, this process never reverses. Galaxies merge locally, forming larger and larger systems bound by gravity. The Milky Way and Andromeda will collide and coalesce into a single, massive galaxy. Beyond that, there will be no new arrivals. Everything else recedes beyond the horizon. Lost to expansion, the future sky will be small. Within this isolated island, stars will continue to form for a while, fueled by the remaining gas. But eventually, that fuel will run out. The last stars will be small, dim red dwarfs, burning slowly for trillions of years. When they die, they will not be replaced. After that, the universe enters a long twilight. White dwarfs cool and fade. Neutron stars spin down. Black holes dominate the mass budget, quietly orbiting in the dark. Dark energy does not interfere with these local processes. It does not tear apart atoms or disrupt orbits in a cosmological constant universe. It simply ensures that nothing new ever arrives and nothing lost is ever recovered. Isolation becomes permanent. This future is sometimes called the heat death, but the term is misleading. Heat death implies thermal equilibrium, a uniform temperature everywhere. In an accelerating universe, equilibrium is never fully reached. Space continues to expand. Horizons persist. Entropy increases, but always within disconnected regions. The universe does not settle. It drifts. Over unimaginably long timescales, black holes themselves will evaporate through quantum processes, radiating away their mass in faint trickles of energy. The timescales are absurd, far longer than the current age of the universe. But dark energy is patient. When the last black hole evaporates, what remains is a thin soup of particles, stretched across an enormous, expanding volume. Energy density approaches zero. Temperature approaches absolute zero. And still, space expands. This is not an ending that arrives. It is an ending that asymptotically approaches, never quite completing, never resolving into a final state. The universe becomes emptier, colder, and darker, but never stops changing in this future. Complexity is impossible. There are no gradients to exploit, no energy flows to tap, no structures to sustain information processing. The universe becomes hostile, not through violence, but through indifference. Dark energy ensures this outcome by removing the possibility of renewal. There is a quiet cruelty in this, not because suffering persists, but because meaning fades. Stories require change, contrast, causality. An eternally expanding, thinning universe offers none of these, and yet, from another perspective, this future is peaceful. No catastrophes, no final collapse, just endless expansion, carrying remnants of a once rich cosmos into ever greater separation. Which perspective is correct? That depends on what you value. Dark energy does not care, but there is a deeper question hiding here, one that goes beyond fate. Why does the universe have a future at all? Why does time extend forward instead of ending? Why is there something rather than nothing? And why does that something persist, stretched thinner and thinner, instead of disappearing? Dark energy does not answer these questions, but it reframes them. It suggests that the universe is not built to reach a goal. There is no final equilibrium, no designed endpoint. There is only evolution under fixed, or perhaps not so fixed, rules. We exist during a brief, luminous interval, when stars shine, galaxies form, and information flows freely. Dark energy guarantees that this interval is temporary, that does not make it meaningless. If anything, it makes it rare. Every moment of structure, every act of understanding, occurs against the backdrop of an accelerating void. We are patterns riding a wave of expansion, aware briefly that the wave exists. The last light of the universe will not be dramatic. There will be no observers left to mark it. No record will remain. But now there is light, and there are minds capable of asking why the universe behaves as it does. Dark energy may shape the end, but it also defines the conditions that made this moment possible. Dark energy confronts us with a paradox that feels more philosophical than physical. The universe is expanding faster and faster. Structures are dissolving. Information is being lost beyond horizons. Yet the universe does not end. It does not collapse into nothingness. It does not tear itself apart, at least not in the simplest models. It persists. This persistence is strange in human intuition. Acceleration implies instability. Systems that run away usually break. Engines overheat. Orbits decay. Structures fail. But the universe accelerates and remains internally consistent, obeying equations that seem almost indifferent to their implications. Dark energy does not drive the cosmos toward a conclusion. It drives it away from one. This raises a subtle question. Is expansion a process or a condition? In everyday physics, motion is something that happens in space. But cosmic expansion is not motion through space, it is the evolution of space itself. There is no external frame in which the universe is moving. There is no outside into which it expands. Space simply keeps being created. If dark energy is truly a property of the vacuum, then expansion is not something imposed on the universe. It is what the universe naturally does when left alone. Matter and radiation are temporary disturbances, ripples on an underlying tendency toward growth. This flips our intuition upside down. Instead of asking why the universe expands, we might ask why it ever slowed enough for structure to form at all. Why gravity had its long, productive era. Why galaxies, stars, and life were allowed to exist before the vacuum reclaimed dominance. The early universe offers a clue. At the beginning, space expanded at an absurd rate during a period known as inflation. In a fraction of a second, the universe ballooned exponentially, smoothing out irregularities and setting initial conditions for everything that followed. Inflation ended, expansion slowed. Inflation slowed, structure formed. Now, billions of years later, acceleration has returned, gentler, quieter, but persistent. This symmetry is unsettling. It suggests that accelerated expansion may be the default state of the universe, that the era of galaxies and stars was an intermission between two phases of vacuum-driven growth. If so, then dark energy is not an anomaly. It is a reminder. This perspective dissolves some of the mystery while deepening another. If acceleration is natural, why does it take the particular form we observe? Why this value? Why this timing? Why this universe? Physics excels at explaining how systems evolve given certain rules. It struggles with why those rules are chosen. Dark energy sits precisely at that boundary. Some see this as evidence that explanation has limits, that not every parameter can be derived. Some values may simply be facts about our universe, like the number of dimensions or the charge of the electron. Others see it as a sign that we are missing something profound, a principle, a symmetry, a deeper layer of description that would make dark energy inevitable rather than arbitrary. Perhaps the vacuum is not empty, but structured, with metastable states and transitions we have not yet observed. Perhaps our universe is slowly relaxing toward a lower energy configuration, and acceleration is a symptom of that relaxation. Or perhaps we are overthinking it. The universe does not owe us a reason, and yet we continue to ask, because understanding the universe is not just about prediction. It is about coherence, about fitting ourselves into a story that makes sense of existence. Dark energy resists narrative closure. It offers no climax, no resolution, only continuation. And that continuation is what makes it unsettling. A universe that ends in fire or collapse invites meaning through finality. A universe that expands forever denies that comfort. It leaves questions unanswered, stories unfinished. In such a universe, meaning cannot be imposed from the outside. It must be generated locally. In this light, dark energy does something unexpected. By guaranteeing that the universe will not provide an ultimate conclusion, it shifts responsibility inward. Meaning becomes a property of observers, not of cosmic destiny. This is not a scientific statement, but it is a consequence of the science. We exist in a universe where the largest scale dynamics are driven by something we barely understand, something that will eventually erase evidence of everything that came before. And still, for now, the universe is legible. Galaxies trace filaments. Light carries information. Laws of physics remain stable enough to be discovered, Dark energy may one day make cosmology impossible, but today it has not. That makes this moment extraordinary. Not because we are central, but because we are early enough to see. If dark energy teaches us anything, it is humility. We have learned to read the universe with astonishing precision. We can trace its history from fractions of a second after the beginning to the slow fade of its distant future. We can predict eclipses, model black holes, detect ripples in space-time itself, and yet the dominant component of the cosmos remains a question mark. Dark energy does not violate our equations. It fits neatly into them. That is what makes it so disturbing. It works too well while explaining nothing. A single term added to Einstein's equations accounts for acceleration, horizons, fate, and then refuses to elaborate. It is a solution without a story. Physics is not accustomed to this. Historically, successful descriptions have pointed toward deeper layers. The orbit of Mercury led to relativity. Atomic spectra led to quantum mechanics. Anomalies open doors. Dark energy closes them. Every new measurement tightens constraints, pushing us toward the simplest explanation: a constant vacuum energy. No evolution, no structure, no hidden dynamics, just a number. If this is correct, then the universe's largest scale behavior is governed by a parameter that cannot be derived, only measured, a value written into reality without justification. That possibility challenges the philosophy of science as much as its mathematics. It suggests there may be aspects of the universe that are contingent rather than necessary, that not everything follows from deep principles. Some things may simply be. This does not mean science has failed. It means science has reached a boundary. Beyond that boundary may lie theories we have not yet conceived. Or it may lie nothing at all, no further explanation, only acceptance. Dark energy forces us to consider both. There is a strange parallel here to the human experience. We seek reasons, causes, narratives that justify existence. Sometimes we find them, sometimes we do not. The universe may be similar. Dark energy may be telling us that the cosmos does not care whether it makes sense to us, that it unfolds according to rules that allow understanding but not necessarily completion. And still, the pursuit matters, because in trying to understand dark energy, we sharpen our tools, refine our theories, and probe the limits of knowledge. Even if the answer is silence, the act of asking reshapes us. We are creatures in an accelerating universe, aware of the acceleration, able to measure it, able to wonder about its meaning. That alone is remarkable. One day, dark energy will push distant galaxies beyond reach. The evidence of expansion will fade. The clues we use today will vanish. The future observers, if any exist, will inherit a universe that looks simpler than it truly is. They may never know what was lost, but we know now. We live at a moment when the universe is still open enough to be studied, still structured enough to reveal its history, still young enough to carry the memory of its own beginning. Dark energy threatens that openness, but it has not taken it away yet. The silence it promises is still far off. There is something quietly defiant about structure in an accelerating universe. Galaxies should not exist for long. Stars should be temporary accidents. Life, especially, should be fleeting. An improbable arrangement of matter fighting entropy on a planet, orbiting a star that will one day burn out. And yet, here we are, in a universe increasingly hostile to complexity, surrounded by evidence that complexity once flourished everywhere. Dark energy sets the stage against which this defiance unfolds. As expansion accelerates, it becomes harder for matter to come together. The universe actively discourages organization. Every successful structure, every galaxy, every star, every molecule is a small rebellion against a cosmic trend toward isolation and dilution. This perspective reframes the story of the universe. The grand narrative is not one of construction, but of resistance. For billions of years, gravity fought expansion and won locally. It sculpted the cosmic web, pulling matter into filaments and knots. It ignited stars and built galaxies. It created environments where chemistry could grow complex and life could emerge. But gravity was always fighting uphill. As dark energy rose to dominance, the conditions that favored structure began to erode. The cosmic web stopped growing. The formation of massive clusters slowed. The universe crossed a tipping point, where creation gave way to preservation and then to decline. We are living in the afterglow of that peak. This realization is easy to miss because the timescales are immense. On human scales, nothing seems urgent. Galaxies are stable. Stars shine reliably. The sky feels eternal, but on cosmic scales, the era of abundance is already over. Most of the stars that will ever exist have already formed. Most of the galaxies that will ever assemble are already in place. Dark energy ensures that the universe's creative phase is finite. This does not make our existence tragic. It makes it contextual. We are not at the beginning of the universe's story, nor at its end. We occupy a narrow window when the universe is old enough to be understood and young enough to still show its workings. Dark energy defines that window. Without it, gravity might have collapsed the universe too quickly, cutting the story short. With too much of it, the story would never have begun. The value we observe balances the two, just long enough for complexity to bloom. This balance feels intentional, but physics cautions us against reading intention, where selection may suffice. If many universes exist, each with different properties, then only those with such a balance would ever produce observers capable of noticing it. In that view, our surprise is not evidence of design, but of survival. Still, the coincidence lingers. Why does the universe allow this brief rebellion? Why does it permit islands of order to arise in a sea of accelerating emptiness? Dark energy does not answer. It simply waits. As expansion continues, the rebellion loses ground. Interactions become rarer. New structures become harder to build. The universe slowly transitions from a place of formation to a place of memory. Eventually, even memory fades. But for now, the rebellion holds. Stars still shine. Galaxies still collide and merge. Life still reflects on its origins and fate. Against the vastness of dark energy's influence, these may seem insignificant. They are not. They are the only things that push back. In an accelerating universe, existence itself becomes an act of resistance, not against a hostile force, but against an indifferent one. Dark energy does not oppose life. It simply does not care whether life exists at all. And that indifference may be the most unsettling truth of all. Every prediction about the universe's future rests on an assumption so quiet we rarely notice it: that the laws of physics do not change. We extrapolate billions of years forward using equations tested over decades, sometimes centuries. We assume that constants remain constant, that relationships hold, that what governs the cosmos today will govern it tomorrow. Dark energy makes that assumption feel fragile, because dark energy is not just another ingredient, it is the dominant one, and we do not know whether it is truly fixed or merely appears so within the narrow slice of time we can observe. Cosmology is uniquely vulnerable to this uncertainty. In most sciences, theories can be stress-tested through repetition. You can run the experiment again. You can vary the conditions. You can isolate variables. The universe offers no such luxury. We observe one realization of cosmic history unfolding once on timescales that dwarf human lifetimes. When we predict its future, we are not forecasting in the usual sense. We are extending a curve far beyond the region where data exist. That curve is shaped by dark energy. If dark energy is a true cosmological constant, then our predictions are solid. Expansion accelerates smoothly. Horizons stabilize. The universe drifts toward cold emptiness. But if dark energy evolves even subtly, those predictions unravel. A tiny change in its equation of state could alter the expansion rate dramatically over billions of years. What looks like a gentle asymptote could become a runaway. What looks eternal could be temporary. The unsettling truth is that we may never know. Even with perfect instruments, even with flawless data, we are limited by cosmic variance and by time itself. We cannot see the far future. We can only infer it. This places cosmology in a strange position among the sciences. It deals not just with what is, but with what will be on scales where verification is impossible. Dark energy forces us to confront that limitation head-on. It also forces us to rethink the meaning of prediction. Perhaps the goal is not certainty, but constraint. Not knowing exactly what will happen, but narrowing the range of possibilities. In that sense, dark energy has already taught us something profound. It has shown us that the universe's fate is not dominated by matter or radiation or structure, but by the properties of space itself. That alone reshapes our expectations. Long ago, it was reasonable to imagine a universe that would end in collapse, recycling itself into another beginning. Dark energy largely rules that out. The universe will not gather itself back together, at least not under known physics. There will be no cosmic reset. What happens now echoes forever. This permanence is unsettling, but it is also clarifying. It means that the universe's history is a one-way path, shaped by early conditions and carried forward by expansion that never looks back. Dark energy ensures that the arrow of time points relentlessly outward, and yet, despite all this uncertainty, we continue to refine our models. We build better telescopes. We analyze deeper surveys. We argue about parameters that differ only in the third decimal place. From the outside, this may seem obsessive. From the inside, it is necessary. Because even if we cannot predict the universe's ultimate fate with certainty, we can understand the forces that shape it now. And in doing so, we learn something about the nature of reality and about our place within it. Dark energy reminds us that knowledge has limits, but it also reminds us that reaching those limits is part of the journey. There is a strange intimacy in realizing that the universe's fate can be summarized by a symbol, a single letter, W, pressure divided by energy density, a ratio that fits neatly on a chalkboard, yet governs whether galaxies drift gently apart or whether reality itself is torn open. In cosmology, entire futures hinge on numbers that look deceptively simple. This is what it means to live inside an equation. For most of history, humans imagined themselves at the center of cosmic meaning. Then we learned we orbit an ordinary star, in an ordinary galaxy. in a universe that does not seem designed with us in mind. Dark energy pushes that humility even further. It tells us that the grandest story, the long-term evolution of everything, is controlled by parameters that have nothing to do with stars, planets, or life. Life is a side effect. Structure is temporary. The equation does not care. And yet, here we are, able to write that equation down. This is the paradox at the heart of cosmology. The universe is vast, indifferent, and dominated by forces we barely understand. But it is also comprehensible enough, at least locally and temporarily, for minds like ours to emerge and model it. Dark energy does not erase that paradox. It sharpens it, because dark energy suggests that the universe is not trending toward complexity, consciousness, or understanding. It is trending toward dilution, toward simplicity of a different kind, an emptiness so complete that nothing interesting can happen anymore. If intelligence exists elsewhere, it too is temporary. Civilizations rise during brief cosmological windows, do their thinking, and vanish long before the universe settles into its dark energy-driven future. There is no cosmic archive, no permanent record. Everything meaningful happens against a deadline no one notices. This reframes the question of significance. If the universe will not remember, does anything matter? Physics does not answer this, but it forces the question into the open. In a universe destined for endless expansion, meaning cannot be cosmic. It cannot be written into the final state of reality. It must be local, fragile, and transient like structure itself. Dark energy ensures that. And strangely, that may be what makes understanding worthwhile, because the fact that we can measure dark energy at all, that we can detect acceleration, infer invisible components, and reason about the fate of the universe means we occupy a rare position in cosmic history. We live early enough that the universe still reveals its secrets, late enough that structure has matured, briefly enough that awareness matters. This is not a comforting conclusion, but it is an honest one. Dark energy does not make the universe meaningless. It makes meaning temporary. And in a universe where nothing lasts forever, temporary things are all there is. When physicists say they do not understand dark energy, they mean something very specific. They mean that it does not fit into any of the conceptual boxes that have guided physics for centuries. It is not a particle we can count, not a field we can easily quantize, not a force with a clear mediator. It does not live where our intuition lives. Dark energy occupies a stranger category. It is a property of space-time itself, but space-time, as we currently understand it, may not be fundamental. General relativity treats space-time as smooth and continuous. Quantum mechanics treats reality as discrete and probabilistic. Both frameworks work astonishingly well in their own domains. Together, they clash. Dark energy lives exactly at that fault line. If the vacuum truly has energy, then space-time has microscopic structure. It has degrees of freedom. It can store information. It can evolve. In that case, dark energy is not a mystery to be added on top of physics. It is a clue pointing downward toward a deeper layer of reality. This is why dark energy is so tightly bound to the problem of quantum gravity. Any theory that unifies quantum mechanics and general relativity must explain why empty space has the energy it does, and why that energy is so small, so uniform, and so consequential. Some approaches imagine space-time as emergent, arising from more fundamental entities such as entanglement or information. In these views, dark energy could be a macroscopic manifestation of microscopic degrees of freedom reorganizing themselves. Others imagine extra dimensions curled up at scales too small to detect. The energy associated with those dimensions could leak into our universe, appearing as dark energy. Still others propose that the vacuum is metastable, a false ground state that will eventually decay into something more fundamental. If so, the universe could undergo a phase transition, radically altering the laws of physics. That possibility is both fascinating and terrifying. A vacuum decay would propagate at the speed of light, rewriting the rules of reality as it goes. Atoms, chemistry, life, none would survive the transition, and we would have no warning. Dark energy might be a hint that we are not in the true ground state of the universe. There is no evidence that such a decay is imminent, but the fact that we cannot rule it out underscores how little we know. Dark energy is not just an unsolved problem. It is a signpost marking the edge of our understanding. Beyond it lies physics that may look nothing like what we are used to. This is uncomfortable. Science thrives on continuity, on building new theories that reduce to old ones in familiar limits. Dark energy suggests that the deepest truths about the universe may not be continuous extensions of what we know, but conceptual breaks to the vacuum may not be passive. Space-time may not be smooth. Constants may not be constant. If any of this is true, then our current picture of the universe is provisional in a deeper sense than usual. Not just incomplete, but structurally limited. And yet, we are not powerless. By studying dark energy, we test the assumptions we take for granted. We probe whether space-time has dynamics of its own. We ask whether the universe's acceleration is telling us about hidden dimensions, emergent geometry, or the limits of effective theories. Even null results are informative. If dark energy continues to look like a cosmological constant under ever more precise scrutiny, then that itself is a clue. It tells us that the vacuum is astonishingly simple or astonishingly well cancelled. Either option demands explanation. The shape of the unknown matters. Dark energy is not chaos. It is constrained, measured, bounded. It occupies a narrow region of possibility space. Understanding why that region is selected may require new mathematics, new principles, or new ways of thinking about reality altogether. This is not the first time physics has faced such a challenge, but it may be the most profound. Step far enough back, and the universe stops looking dramatic. On the largest scales, it is smooth, uniform, governed by a handful of numbers. Dark energy is one of them, perhaps the most important one. From this long view, galaxies are fleeting ripples. Stars are brief flashes. Life is a momentary configuration of matter that appears, reflects, and vanishes. This perspective can feel bleak, but it can also feel clarifying. Dark energy does not rush. It does not surge or collapse. It acts with patience, measured in billions of years. While everything else changes, stars ignite and die, galaxies collide, black holes merge, dark energy remains steady, stretching space with quiet persistence. It is the background against which all cosmic drama unfolds. This makes dark energy uniquely difficult to conceptualize. It does not behave like a cause in the usual sense. It does not act on objects. It shapes the arena in which objects exist. In that sense, dark energy is closer to a boundary condition than a force. It defines how the universe evolves when nothing else interferes. And when we look far into the future, nothing else will. Matter will thin. Radiation will fade. Only the vacuum will remain, doing what it has always done, expanding. This does not mean the universe is pointless. It means the universe is not about us. Dark energy strips away anthropocentrism more effectively than any discovery before it. It tells us that the cosmos does not culminate in life, consciousness, or understanding. These are local phenomena, emerging briefly under specific conditions. They are not the destination. And yet, their very transience gives them weight. In an eternal universe that accelerates forever, nothing is guaranteed except change and separation. There will be no cosmic memory, no final archive of achievements, no enduring structure to preserve what once was. Meaning, therefore, cannot be deferred to the end of time. It must exist in the moment of experience. Dark energy, in its own indifferent way, forces this realization. We study the universe not because it promises a conclusion, but because it is here now, structured now, intelligible now. The long view does not diminish that, it sharpens it. Because if the universe were static and eternal, understanding might feel optional. In a universe that is accelerating toward isolation, understanding becomes a race against erasure. We are early enough to see the cosmic web, late enough to know it will fade. That combination is rare. Dark energy defines the boundary of our era. It marks the transition from a universe that builds to one that dissolves. We exist on that boundary. And perhaps that is enough. Long before dark energy began its quiet takeover, the universe had already experienced acceleration once before. It was violent, brief, absolute. In the earliest fraction of a second after the Big Bang, space expanded exponentially in an event known as cosmic inflation. Distances doubled again and again in unimaginably short intervals. Quantum fluctuations were stretched to cosmic scales. The seeds of galaxies were planted in the vacuum itself. Then, just as abruptly, it stopped. Expansion slowed. Matter and radiation took over. Structure formed. For decades, inflation and dark energy were treated as separate chapters, one belonging to the universe's birth, the other to its old age. But the more we learn, the harder it becomes to ignore the symmetry. Both involve accelerated expansion. Both appear to be driven by vacuum-like energy. Both dominate when other forms of energy become irrelevant. This resemblance may be a coincidence, or it may be a clue. If inflation was powered by a field trapped in a high-energy state, then dark energy could be the same mechanism operating at a vastly lower energy scale. Two phases of the same underlying physics, separated by billions of years. In this view, the universe has always been prone to acceleration. What we call the normal era, dominated by matter, stars, and galaxies, may be the exception, not the rule. That is a humbling thought. It suggests that everything we find familiar is a temporary deviation from the universe's preferred behavior. Space wants to expand. Structure only emerges when conditions briefly allow it. If this is true, then dark energy is not the end of the story. It is the return to baseline. This possibility opens unsettling doors. If the early universe transitioned out of inflation, could the late universe transition out of dark energy? Could the vacuum change state again? Some models suggest yes. In these scenarios, dark energy is not eternal. It is a metastable phase that will eventually decay, perhaps gently, perhaps catastrophically. The universe could shift into a new regime with different laws, different constants, different possibilities. We have no evidence that such a transition will occur. but we also have no fundamental reason to rule it out. The vacuum has surprised us before. This uncertainty highlights a recurring theme in cosmology. The universe is not obligated to remain in the state we observe today. Its history includes dramatic transitions. Its future may as well. Dark energy may be stable, or it may be provisional. We cannot yet tell the difference. What we can say is that acceleration appears twice in the universe's timeline, once at the beginning, once at the end. That symmetry demands attention. It hints that the vacuum is not passive, but active. That empty space has phases, properties, and perhaps a life cycle of its own. If so, then dark energy is not just about expansion. It is about the nature of nothingness. And nothingness, it turns out, may be the most dynamic thing of all. We often speak of the laws of physics as if they were eternal truths etched into the fabric of reality. Dark energy invites us to question that assumption. If the vacuum can drive acceleration, if empty space has energy that dominates the universe, then the vacuum has structure. And if it has structure, it can change. This is a deeply uncomfortable idea. In everyday physics, laws are stable. Constants do not drift. Forces do not fade. But cosmology already hints that this stability may be local rather than universal. Inflation suggests that the early universe passed through a phase governed by different effective laws. Symmetries may have broken. Constants may have settled into their current values. Dark energy could be another phase in that process. If the vacuum can exist in multiple states, each with its own energy density, then what we call laws may be emergent properties of a particular vacuum configuration change the vacuum, and the laws change with it. This turns physics inside out. Instead of laws determining the vacuum determines the laws. Such a framework would explain why certain constants appear finely tuned. They are not uniquely determined. They are selected by the vacuum state our universe happens to occupy. Dark energy, in this context, is not a mysterious add-on. It is the signature of our vacuum. But this view carries a heavy price. If laws are contingent, then ultimate explanation may be impossible. There may be no deeper reason why the vacuum has the properties it does. It may simply be one possibility among many. Science can map the consequences of those properties. It may not be able to justify them. This is not a failure of science. It is a limit of what explanation means. Dark energy pushes us toward that limit. And yet, even within this uncertainty, patterns remain. The universe is not arbitrary chaos. It evolves according to consistent rules, at least within each phase. We can model those rules, test them, and use them to predict observable phenomena. The fragility lies not in the laws themselves, but in our assumption that they must be absolute. Perhaps they are not. Perhaps the universe is layered, with stable regimes punctuated by transitions we have barely glimpsed. Dark energy may be the marker of the current regime, a sign that we are living inside a particular phase of space-time. If so, then the future of the universe is not just a question of expansion rate, it is a question of stability. Will the vacuum remain in this state indefinitely? Or will it transition, altering the very rules that govern matter and energy? We do not know. But the fact that we can even ask the question is remarkable. Dark energy has not destroyed predictability. It has revealed its conditional nature. And in doing so, it has shown us that the universe is deeper, stranger, and more fragile than we once imagined. There is a peculiar vertigo that comes from thinking too far into the future. not just thousands or millions of years ahead, but billions, trillions, numbers so large they lose their intuitive meaning. Dark energy forces us into that vertigo because it defines the long-term trajectory of everything that exists. It tells us that the universe is not heading toward renewal, it is heading toward separation. As time stretches on, interactions become rarer. Causally connected regions shrink. Each island of matter becomes more isolated, more self-contained, more alone. The universe does not end with a bang or a crunch, but with a quiet thinning of relationships. This is not merely a physical process. It is a conceptual one. Cosmology has always been about connection, how distant objects relate, how the past informs the present, how light links events across time. Dark energy undermines that framework by steadily severing those links. The universe becomes less narratable. At some point in the far future, even the notion of cosmic history will break down. Observers will be unable to reconstruct the past because the evidence will be gone. The universe will appear static and eternal, not because it is, but because it has erased its own memory. We live before that erasure is complete. We stand at the edge of time, with access to a deep cosmic past and a long cosmic future, able to see both directions at once. This position is not guaranteed. It is contingent on when we exist. Dark energy defines that contingency. It ensures that there is a limited window during which the universe is both old enough to have a story and open enough to reveal it. This realization reframes the act of cosmology itself. Studying the universe is not just an intellectual pursuit, it is a race against cosmic forgetting. We map galaxies not just to satisfy curiosity, but because one day those maps will be impossible to make. We measure expansion not just to test theories, but because the expansion will eventually hide its own traces. Dark energy does not forbid understanding. It places a deadline on it. This deadline is not dramatic. It does not arrive with warning signs or countdowns. It unfolds gradually, invisibly, as light from distant regions stretches and fades. And yet, its consequences are absolute. The universe will not always be knowable. This is perhaps the most profound implication of dark energy. Not that it will end the universe, but that it will end cosmology. There will come a time when the universe's deepest truths are inaccessible, not because they are false, but because they are unreachable. We exist before that time, and that matters. Dark energy does not threaten existence directly. It threatens context. By stretching space and isolating regions of the universe, it ensures that nothing global can last. Not structures, not histories, not shared meaning across cosmic scales. Everything becomes local. Everything becomes temporary. This is easy to misunderstand as nihilism. It is not. It is a shift in scale for most of human history. Meaning was anchored locally, family, tribe, land, sky. The cosmos was a backdrop, not a participant. Modern cosmology expanded that backdrop into a story of origins and fate, offering a sense that meaning might be written into the universe itself. Dark energy quietly withdraws that offer. It tells us that the universe does not converge toward significance, it diverges away from it. Any meaning that exists must arise within bounded regions, during finite intervals, sustained by fragile structure, in an accelerating universe. Permanence is not a feature, but that does not make meaning illusory. It makes it emergent. A pattern that exists for a time is not less real because it ends. A thought is not meaningless because it fades. A civilization is not irrelevant because the universe will not remember it. Dark energy forces us to abandon the idea that meaning requires eternity. Instead, it suggests that meaning is something that happens briefly, locally, against the odds. This is consistent with physics, even if it feels uncomfortable. Entropy increases. Structures form and dissolve. Complexity blooms where conditions allow and vanishes when they do not. Dark energy accelerates this process on cosmic scales, but it does not invalidate what occurs within it. If anything, it sharpens it. Because in a universe that does not guarantee persistence, every instance of understanding is rare. Every moment of coherence is borrowed time. This perspective changes how we see ourselves in the cosmic story. We are not the point of the universe. We are witnesses inside it. And witnesses matter not to the universe, but to each other. Dark energy does not erase that. It frames it. The accelerating expansion ensures that no ultimate cosmic audience exists. There is no final reckoning where everything is weighed and preserved. There is only what happens while it can. This places responsibility where it has always belonged, within the present. Physics does not tell us how to live, but it tells us something important about the conditions under which living and understanding is possible. Dark energy tells us those conditions are temporary, and that is not a tragedy. It is a constraint. Within constraints, meaning becomes deliberate rather than inherited, chosen rather than guaranteed. The universe may be indifferent, but indifference does not negate significance. It relocates it. At the heart of everything we have said about dark energy lies a simple, unsettling truth. Nothing dramatic is happening. No explosions announce its presence. No catastrophic failures betray its influence. The universe looks much the same today as it did a few billion years ago, and it will look much the same billions of years from now, just slightly emptier, slightly colder, slightly more isolated. Dark energy works by subtlety. It is the quiet center of the cosmic story, exerting its influence not through forceful intervention, but through patience. While stars blaze and die, while galaxies collide, while black holes warp space-time into extremes, dark energy simply stretches the stage. This is why it took so long to notice. For most of cosmic history, dark energy was irrelevant. Matter dominated. Gravity ruled. Expansion slowed. The universe built complexity with abandon. Only when matter thinned enough did dark energy rise from insignificance to dominance. Only when the universe was already old did its fate become sealed. We arrived just in time to see the transition. This coincidence is not comforting. It means we are close to a turning point that is not reversible. The universe has already passed its peak of structural richness. What remains is a long, quiet unwinding. And yet, the quiet is not empty. The same laws that govern expansion also allow stability. Within gravitationally bound systems, dark energy is powerless. Atoms remain intact. Planets orbit. Life continues, at least for a while. The universe is not being torn apart. It is being spaced out. This distinction matters, because it means that the end of cosmic connection does not arrive all at once. It arrives unevenly. Locally, everything seems fine. Globally, everything is drifting apart. This mismatch between local experience and global reality is one of the most profound lessons dark energy offers. We live inside a universe whose overall trajectory is toward isolation, but whose local environments can remain rich, structured, and meaningful for extraordinary lengths of time. Both statements are true. Dark energy teaches us to hold them simultaneously. The universe does not need to rush to an ending to be finite in what it offers. The fact that it expands forever does not mean it offers infinite opportunity. Opportunity depends on density, interaction, energy flow. Dark energy slowly erodes all three. This erosion is gentle enough that it feels abstract, but abstraction does not diminish consequence. In the far future, there will be nothing to mark the passage of cosmic time. No background radiation, no distant galaxies, no large-scale structures evolving, only isolated systems, drifting in a universe whose vastness exceeds memory. Dark energy is the architect of that quiet, and it is already at work. When the universe is viewed from its far future, one question becomes unavoidable: what remains? Not what ends, because dark energy ensures that endings are diffuse and uncelebrated, but what survives longest. What patterns persist when expansion has done nearly all it can do? The answer is not galaxies. Galaxies are social structures. They require interaction, mergers, inflows of gas. Dark energy cuts those supply lines early. Once isolation sets in, galaxies age quickly. They burn what fuel they have and then grow quiet. Stars last longer, but not forever. The final generation, small, dim red dwarfs, will burn for trillions of years, slowly converting hydrogen into helium. Their longevity is impressive, but it is not immunity. Even they eventually exhaust their fuel. After them, stellar remnants dominate, white dwarfs cooling into darkness, neutron stars spinning down, black holes quietly orbiting one another. Of all structures, black holes endure the longest. They are gravity distilled, matter crushed into minimal form. In a universe stripped of complexity, they are the last monuments to an earlier era of structure. And yet, even black holes are not eternal. Quantum mechanics demands that they radiate. Hawking radiation bleeds them dry over absurd timescales, numbers so large they resist comprehension. But given infinite time, even black holes fade. Dark energy does not stop this. It ensures it happens in isolation. When the last black hole evaporates, there is no audience, no environment rich enough to notice, no structure left to be affected. What remains is space, expanding, cooling, thinning. Dark energy does not end at that point. It does not turn off once the universe is empty. It continues to do what it has always done, stretching space-time, increasing distances, enlarging the void. In a strange way, dark energy outlives everything else. Matter comes and goes. Radiation fades. Structure collapses or evaporates. But the vacuum remains, asserting its preference for expansion long after there is anything left to expand from. This is the ultimate asymmetry of the universe. Everything that happens is temporary. The stage is permanent. And yet, even this permanence is deceptive. If dark energy is truly constant, then the universe asymptotically approaches emptiness, but never quite reaches a final state. There is always more later, even if later looks indistinguishable from before. Time does not end, it thins. This is a universe without punctuation. No period, no final line, just continuation. This vision is unsettling because it denies closure. It offers no cosmic resolution, no final synthesis. The universe does not sum itself up, it simply moves on. Dark energy guarantees that, and in doing so, it quietly tells us something important about our own moment in cosmic history. We exist when things still happen, when complexity still emerges, when cause and effect still weave rich patterns that will not always be true, and that makes now different, not privileged, but fleeting. As the universe stretches toward a future of isolation, a strange inversion occurs. The biggest questions become the quietest. In the early days of cosmology, the mysteries were loud. What are stars? Why do galaxies exist? How old is the universe? Each answer revealed deeper structure and richer complexity. The universe felt like a puzzle eager to be solved. Dark energy changes the tone. It introduces questions that do not escalate into new phenomena, but instead collapse inward. Questions about limits, about finality, about whether explanation itself has an endpoint. Why does empty space have energy? Why is that energy so small? Why does it dominate now? These questions do not lead neatly to experiments or technologies. They resist iteration. They hover at the edge of what science can address. And that is precisely why they matter. Dark energy confronts us with the possibility that not all mysteries are meant to unfold into deeper layers. Some may be terminal, not in the sense of being unsolvable, but in the sense of being foundational. The value of dark energy may simply be a fact about this universe. If that is true, then the universe is not maximally intelligible, it is intelligible enough. Enough to form stars, enough to build galaxies, enough to give rise to minds that ask questions, but not enough to justify itself. This realization is difficult for a species that has grown accustomed to progress. We expect tomorrow's theories to explain today's anomalies. We expect understanding to deepen without bound. Dark energy hints that this expectation may be misplaced. It may mark a point where explanation gives way to description, and description gives way to acceptance. That does not diminish science. It clarifies its role. Science is not a promise that everything will make sense. It is a method for discovering how much sense the universe allows. Dark energy defines that boundary. And yet, even here, there is movement. Physicists continue to search for patterns, for hidden symmetries, for subtle deviations that might reveal dark energy's true nature. New surveys map the cosmos with unprecedented fidelity. New theories explore the vacuum from fresh angles. The work continues not because success is guaranteed, but because curiosity persists. This persistence is itself remarkable. In a universe that does not care whether it is understood, understanding still arises. Against the vastness of cosmic indifference, minds assemble equations, build telescopes, and argue about the fate of everything. Dark energy does not prevent that. It contextualizes it. The last questions may never be answered, but they are still worth asking. There is a moment in every great journey when the landscape behind you disappears. Not because it has changed, but because distance has made it unreachable. Dark energy ensures that the universe itself will experience this moment, not all at once, but piece by piece, horizon by horizon. Beyond the cosmic event horizon, reality does not end. It simply stops being part of our story. Those regions continue to evolve. Stars continue to burn. Galaxies continue to age. But they do so without causal connection to us. No signal from there can ever reach here. No influence can cross the expanding gulf. They might as well be different universes. This is one of the most counterintuitive consequences of acceleration. The universe does not fragment through violence or collapse, but through expansion so relentless that connection becomes impossible. Dark energy turns distance into destiny. In this future, the concept of the universe fractures. There is no longer a single, shared cosmos. There are countless isolated domains, each unaware of the others, each limited to its own shrinking bubble of accessible space. This is not the multiverse of speculative physics. It is a multiverse born of separation. Every gravitationally bound system becomes its own island, carrying with it the last remnants of a once connected reality. Within each island, local physics proceeds as usual. Time flows, matter interacts. Life, if it survives, continues to ask questions, but the grand context is gone. No observer will ever again see the universe as a whole. This is perhaps the most radical implication of dark energy. Not that it changes what exists, but that it changes what can be known. It redraws the boundary between reality and irrelevance, not based on importance, but on reachability. Physics has always assumed that, given enough time, information can spread. Light travels. Signals propagate. Causes connect to effects. Dark energy breaks that assumption. It introduces permanent disconnection. And once that happens, certain kinds of knowledge become impossible, not in practice, but in principle. There is no clever workaround. No technology can outrun expanding space. The horizon is absolute. We are accustomed to thinking of horizons as things to be crossed. Mountains climbed, oceans sailed, barriers overcome. The cosmic horizon is different. It is not something you reach. It is something that reaches you. As time passes, it moves inward, enclosing you more tightly, trimming away parts of reality you once could have known. This is a sobering thought. It means that even if intelligence survives for trillions of years, even if technology advances beyond anything we can imagine, the accessible universe will continue to shrink. Knowledge will not accumulate indefinitely. It will plateau, then erode. Dark energy does not destroy civilizations. It outpaces them. And yet, for now, the horizon is far away. The universe is still vast and open. We can still see deep into the past. We can still map large-scale structure. We can still infer the shape of cosmic history. This openness is temporary, which makes the present extraordinary. Not because it is central, but because it is connected. There is a particular kind of loss that comes not from destruction, but from narrowing. Dark energy does not erase the universe all at once. It removes vantage points. It steals perspective. Over time, it ensures that no observer, no matter how long-lived, how advanced, how curious, can ever again see the cosmos in its full context. This loss is subtle because it happens unevenly. Local structures remain rich for an extraordinarily long time. Stars continue to orbit. Remnants interact. If life endures, it may thrive within gravitationally bound islands for epochs that dwarf human history. But beyond those islands, the universe is quietly slipping away. The cosmic microwave background fades first, stretched beyond detectability. Then distant galaxies disappear, one by one, as their light redshifts past every conceivable instrument. Eventually, even the evidence of expansion itself vanishes. No Hubble flow, no large-scale motion, no reason to suspect the universe was ever different from what is immediately visible. To future observers, the universe will look small, static, and eternal. They will be wrong. but they will have no way of knowing it. This is perhaps the most unsettling implication of dark energy. Not that it shapes the future, but that it rewrites the past. It ensures that future intelligence, no matter how capable, will inherit a universe stripped of its own history. Cosmic archaeology will become impossible. There will be no relic radiation to analyze, no distant supernovae to measure, no large-scale structure to map. The clues we rely on today to reconstruct cosmic evolution will be gone, not hidden, but unreachable. The universe will have lost its autobiography, and with it, a certain kind of truth. This forces us to reconsider what it means to understand the universe. Our current picture of cosmology depends critically on where we exist in time. We are not just observers, we are observers at a special epoch when information about the past is still accessible. This does not make us special in a moral or metaphysical sense. It makes us fortunate in a practical one. Dark energy defines a shrinking window during which the universe can be known as a whole. We live within that window. That fact carries an unexpected responsibility, not because the universe needs us to remember it, but because if memory exists at all, it exists only now. The record we assemble, the measurements, the theories, the stories, will not be recoverable later. They are not cumulative, they are perishable. In a universe governed by dark energy, knowledge has an expiration date. This does not diminish its value. It intensifies it. Understanding the cosmos is no longer just an abstract quest for truth. It is a race against cosmic isolation, a brief opportunity to glimpse the full scope of reality before perspective collapses inward. Dark energy ensures that no final, all-encompassing theory will ever be verified by future observers. The data required will not exist. What we know because we are early. And what we fail to learn, no one else will recover. This is not a reason for despair. It is a reason for urgency. Dark energy never announces its arrival. There is no moment when the universe suddenly feels different. No cosmic tremor that marks the instant acceleration begins to dominate from inside the universe. Everything seems continuous. Stars still rise. Galaxies still glow. Time still flows forward, second by second, as it always has. And yet, beneath that continuity, something irreversible is underway. Dark energy is the invisible hand guiding the universe toward a future without witnesses. It does not rush. It does not destroy. It does not need to. Its power lies in persistence. Given enough time, even the gentlest pressure reshapes everything. Mountains erode. Orbits drift. Connections fade. On the largest possible scale, dark energy is erosion written into space-time itself. This is what makes it so difficult to accept. We are conditioned to recognize danger through disruption. Dark energy offers none. It simply alters the long-term balance of reality, ensuring that separation eventually outweighs attraction, isolation outweighs interaction, forgetting outweighs memory. The universe is not collapsing. It is letting go. In this letting go, there is no malice, no intent. Dark energy is not an enemy, nor a villain. It is not tearing reality apart out of hostility, but out of indifference. It follows its nature, whatever that nature may ultimately be. And that indifference is precisely what unsettles us, because it means the universe is not organized around outcomes we recognize as meaningful. There is no cosmic preference for life, understanding, or continuity. These arise temporarily, under specific conditions, and fade when those conditions dissolve. Dark energy guarantees that they will dissolve, but it also explains why they existed at all. The universe had to expand to cool. It had to cool to form structure. Structure had to exist for stars to shine, for chemistry to complexify, for minds to arise. Dark energy did not prevent this story. It framed it. It ensured that the story would have a beginning, a middle, and if not an end, then a long, quiet dispersal. We exist in the middle, not at the peak of expansion, not at the moment of isolation, but in the narrow era when the universe is still rich enough to support complexity and still open enough to be understood. That is not coincidence in the human sense, it is context. Dark energy defines the boundaries of that context. It tells us that the universe will not always be this way, that what we see now, the web of galaxies, the glow of ancient light, the deep history written across the sky is temporary. This does not cheapen it. It makes it precious. Because nothing in an accelerating universe is guaranteed except change. Everything else, structure, memory, meaning, exists only for a time. And time, in this universe, is not infinite in the ways that matter. Dark energy stretches the future open while thinning it of substance. It ensures that the universe will continue, but not that anything within it will remain connected, remembered, or relevant. Against that vast backdrop, the act of understanding becomes quietly heroic. We measure expansion. We infer the invisible. We name a force we do not understand and admit, honestly, that we do not know what it is, that honesty matters. Dark energy is the universe reminding us that knowledge is provisional, that certainty has limits, and that even the deepest truths may not come with explanations we find satisfying. And yet, we keep looking, because for this brief interval, this fragile, luminous moment, the universe is still speaking. Its message is written not in explosions or catastrophes, but in the slow drift of galaxies and the faint stretching of light, a message that says, "This will not last." And knowing that we listen more carefully, dark energy will have the final say, but it does not erase what came before. It only ensures that what came before mattered when it happened, and that, in an accelerating universe, is everything. One day, long after the last galaxy has slipped beyond the horizon, long after the sky has gone dark and empty, long after even memory has thinned into silence, there will be no one left to know what the universe once was. No witness will remain to confirm that stars once filled the heavens, that galaxies once tangled and danced, that minds once looked outward and asked why. Dark energy will not mark this moment. It will not pause. It will not acknowledge the loss. Space will keep expanding. And yet, right now, the universe is not empty. Right now, space still carries light. Right now, history is still visible. Right now, the equations still connect the present to the beginning. And right now, someone is listening. That may be the most extraordinary fact of all. Not that the universe exists, not that it expands, not even that it is tearing itself apart, but that, for a brief and fragile interval, it produced beings capable of noticing. Dark energy will erase the evidence. It will scatter the stage and dim the lights. It will ensure there is no final archive, no cosmic memory, no eternal record. But it cannot erase this moment, the moment when the universe became aware of its own fate. Meaning was never written into the cosmos. It was written inside it, in minds that knew they were temporary, and chose to understand anyway. The universe does not need to remember us for this to have mattered. because meaning was never waiting at the end of time. It existed here, now, while the universe was still listening.